Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from Tencent Youtu Lab, Youtu-Agent, scaling agent productivity with automated generation and hybrid policy optimization. Large language models are getting better at acting like general-purpose agents, but turning them into reliable real-world systems is still painful. Today, building a strong agent means lots of handcrafted tool wiring, prompt tweaking, and debugging. And once you finally deploy that agent, it usually stays frozen. It doesn't adapt to new tasks or environments unless you pay for expensive fine-tuning. This paper asks, can we automate both how agents are built and how they keep getting better? The authors highlight two main bottlenecks. First, configuration cost. You have to pick tools, write Python wrappers, integrate APIs, and craft prompts. It's a craftsman process that doesn't scale. Second, static capabilities. Once deployed, agents don't naturally improve. You can tweak prompts or run supervised fine-tuning or RL, but that needs lots of labeled data, GPU time, and often becomes unstable on long-horizon tasks. Youtu-Agent is designed to attack both of these pain points head-on. Youtu-Agent is a full-stack framework for building and improving LLM agents. It gives you a clean modular architecture, plus automation that can generate agents from just a high-level description. On top of that, it adds a hybrid optimization system, a lightweight practice mode that improves behavior without touching model weights, and a full reinforcement learning pipeline for deeper gains. Importantly, all of this is built on open-weight models, so you don't need proprietary APIs like GPT or Claude. At the core of Youtu-Agent is a three-layer architecture. The environment layer wraps backends like browsers, operating system shells, or code sandboxes, exposing state and primitive actions. On top of that, the tools layer defines higher-level operations, from clicking DOM elements to running math or text utilities, and even external MCP services. Finally, the agent layer is the LLM planner and executor, running a perceive, reason, act loop. A context manager keeps the working memory compact by pruning stale information, which is crucial for long interactions. Because these layers are decoupled, the same tools and agents can run across different environments with minimal changes. Youtu-Agent standardizes everything in YAML. An agent configuration declares which environment to use, which toolkits are active, what system instructions guide the LLM, and how context is managed. This human-readable format makes it easy to prototype, share, and version different agent variants. Crucially, this same YAML schema is also the target for the automated generation mechanisms, so both humans and meta agents are speaking the same configuration language. Beyond just running agents, Youtu-Agent is built to help them improve. The eval component runs agents on benchmarks and reports standardized metrics. The agent practice module lets agents practice on small datasets and distill what they learn into context, without any gradient updates. And the agent RL module connects Youtu-Agent to modern RL frameworks for full-scale, end-to-end training. Together, these pieces turn the framework from a static executor into a system that can continuously evolve. To cut configuration costs, Youtu-Agent can generate agents automatically from a short natural language description. It offers two paradigms. Workflow mode is a fixed, deterministic pipeline that works well for routine tasks. Meta-agent mode is more flexible. It spins up an architect agent that can search for tools, create new ones, ask the user clarifying questions, and finally assemble the full YAML configuration. In both cases, the end product is a deployable agent config with tools, prompts, and environment wired up. Workflow mode is like a factory line for agents. First, it parses the user's request and decomposes it into concrete technical requirements. Second, it searches the existing toolkit library, and if something is missing, uses an LLM to synthesize new Python tools, complete with signatures, docstrings, and unit tests. Third, it performs prompt engineering to craft system instructions that match the tools and task. Finally, it assembles everything into a complete YAML configuration. This gives you a reproducible way to spin up agents for common task categories. Meta-agent mode is designed for messy, real-world requests that don't fit a rigid pipeline. Here, an architect agent is given a set of meta tools. It can search the tool library, create new tools, ask the user follow-up questions, and finally create the agent configuration. It dynamically decides when to clarify requirements, when to reuse existing tools, and when to synthesize new ones. The result is a more flexible, interactive generation process that can handle complex or underspecified tasks. To see meta-agent mode in action, consider a user who wants an agent that summarizes today's trending multi-agent papers and downloads the PDFs. The architect agent first searches the library and finds an archive toolkit that can download papers. It notices there's no tool for fetching daily trending lists, so it calls create tool to synthesize a fetch daily papers function using external API docs as guidance. Finally, it calls create agent config to wire these tools into a papers analyzer agent with appropriate instructions. All of this happens automatically from a single natural language request. The Agent Practice module is built on training-free group relative policy optimization, or training-free GRPO. Instead of updating model weights, the agent runs multiple rollouts per task on a small set of examples. An LLM evaluator then compares these trajectories within each group, identifying what worked and what failed. Rather than computing numeric advantages, it writes down a semantic advantage, a textual description of what to do more of and what to avoid. This distilled experience becomes a kind of policy update in text form. Once practice is done, the system doesn't touch the model weights at all. Instead, it stores the distilled experiences as text snippets. During online testing, these snippets are injected into the agent's context, effectively steering its reasoning. The authors describe this as a textual LoRa. It behaves like a low-rank adaptation, but purely in the prompt space. Because there are no gradients, this approach works even for closed or API-only models. For applications that need deeper, lasting gains, Youtu-Agent offers a full RL pipeline. The framework wraps its custom agent logic and connects it to RL systems like VERL through Agent Lightning. The focus is on two hard problems: scaling to large distributed setups and keeping training stable on long-horizon tasks. With this design, you can train Youtu-Agent-based systems end-to-end across many GPUs, while still using the same environment and tool abstractions as in inference. On the infrastructure side, the authors wrap agent environments behind RESTful APIs, so rollouts can be distributed and load-balanced like standard web services. They use Ray for concurrency, allowing many workers to generate trajectories in parallel. To avoid deadlocks and crashes, they add layered timeout logic at the tool, step, and episode levels. Together, these changes make it possible to scale Agent RL to 128 GPUs while keeping the system responsive and robust. Long-horizon agents often suffer from entropy explosion, where the policy drifts into repetitive or nonsensical tool calls. Youtu-Agent tackles this at the algorithm level. It filters out invalid or anomalous tool calls so the policy doesn't learn degenerate patterns. It reduces off-policy updates and removes batch shuffling to avoid overfitting stale experience. And it corrects bias and advantage estimation for turn-level GRPO. The result is smoother KL divergence, controlled gradients, and steadily improving critic scores and validation accuracy. To test the overall framework, the authors adopt a plan and execute pattern. A planner agent decomposes tasks and schedules subtasks, while specialized executors handle the actual work. All of this runs on open-source DeepSeek v3 models with no proprietary APIs. They evaluate on challenging web navigation and QA benchmarks, showing that the architecture and tools are strong enough to compete with state-of-the-art systems while remaining fully open. On WebWalker QA, which stresses multi-step web navigation and reasoning over real websites, Youtu-Agent reaches 71.47% pass-at-1 accuracy. On the text-only subset of Gaia, a broad benchmark for general AI assistants, it achieves 72.8%. These results rely on a mix of web search, crawling, document parsing, and code execution tools. Together, they position Youtu-Agent as a strong, open-source baseline that doesn't depend on closed, proprietary models. To systematically test automated agent generation, the authors build their own benchmark, Agent Gen 80. It contains 80 task descriptions, from simple retrieval to complex multi-step automation. They evaluate three aspects: whether the generated YAML is structurally valid, whether synthesized tools compile and run correctly, and whether the resulting agent can actually complete the task. This lets them compare the deterministic workflow mode against the more flexible meta-agent mode. On Agent Gen 80, the workflow mode nails configuration validity at 100%, thanks to its deterministic pipeline, and reaches about 81% tool executability. The meta-agent mode is almost as robust, with 98.75% valid configs and slightly higher tool executability. When you look at full task completion, meta-agent pulls ahead, about 69% versus 65% for workflow. That suggests the extra flexibility of an architect agent can translate into better end-to-end behavior, especially on more complex tasks. The authors test training-free GRPO on hard math benchmarks, AIM 2024 and 2025. They start from a React-style agent with a code interpreter tool. For practice, they sample just 100 problems from the DAPO Math 17K dataset and run 3 epochs of group rollouts. There are no gradient updates. The agent only refines its textual experience. Despite this tiny budget, the method yields measurable gains on both AIM benchmarks, showing that even small-scale practice can pay off. With ground truth answers available, training-free GRPO boosts DeepSeek v3.1 Terminus by 2.7 percentage points on AIME 2024 and 5.4 points on AIME 2025 relative to a React baseline. Even without labels, the method still delivers strong results, which is important for domains where annotations are scarce. The estimated cost is around $18, compared to $10,000 to $20,000 for RL methods that fine-tune a 32 billion parameter model. Training curves show that accuracy rises steadily while the average number of tool calls drops, meaning the agent is not just getting better, it's getting more efficient. For full RL, the authors train Qwen 2.5 to 7b Instruct on math and code reasoning tasks, using a sandboxed code interpreter as an external tool, similar to the retool setup. After 500 RL steps, AIM 24 accuracy jumps from 10% to 45%, and AIM 25 rises from 9% to 31%. These are large absolute gains, showing that the RL pipeline can significantly upgrade a mid-sized open-source model's reasoning ability when combined with tool use. They also evaluate RL on information-seeking tasks, using a local Wikipedia 2018 retrieval service as a tool. Training Qwen 2.57b Instruct with this setup yields consistent improvements across Trivia QA, Pop QA, Natural Questions, MusaQ, Hotpot QA, Bamboogle, and 2Wiki Multihop. The gains range from 8 to 21 percentage points, with Natural Questions seeing the largest jump. This shows that the same RL infrastructure can boost both reasoning-heavy math tasks and search-heavy QA tasks. In terms of raw efficiency, the optimized Agent RL module is about 40% faster per training iteration than the official Agent Lightning v0.2.2 release. Most of this comes from better concurrency control, restful environment wrapping, and robust timeout handling. Rollout generation, which is often the bottleneck in Agent RL, is significantly sped up. This makes large-scale experiments, like training on 128 GPUs, much more practical in real-world settings. Youtu-Agent sits in a growing ecosystem of agent frameworks, like MetaGPT, AutoGen, and ChatDev, which focus on multi-agent collaboration and role assignment. What's different here is the emphasis on automatically generating not just prompts, but also tool code and full configurations. On the optimization side, it unifies prompt-style verbal reinforcement, training-free practice, and full RL. The goal is to cover the entire lifecycle of an agent, from initial design through execution to continuous learning. To make the framework tangible for end users, the authors build TIP, an on-device desktop assistant that embeds Youtu-Agent. TIP can load existing agent configs to handle shell commands, file management, and more, all within a unified interface. It proactively captures screen and text context to suggest intents, so users don't have to copy and paste. A GUI agent can automate mouse and keyboard actions, then save these as reusable skills. Because it supports on-device models, TIP keeps user data local and private, while still leveraging the full power of Youtu-Agent. Stepping back, the main contributions of Youtu-Agent are clear. First, a clean, modular architecture with YAML configs that make agents easy to compose and reuse. Second, 2 automated generation modes that can turn a high-level description into a working agent, including tools and prompts. Third, a training-free GRPO practice module that offers cheap, label-light performance gains without touching model weights. And fourth, a robust Agent RL pipeline that scales to large clusters while staying stable on long-horizon tasks. Quantitatively, Youtu-Agent delivers strong numbers. It reaches over 71% on WebWalker QA and nearly 73% on Gaia's text-only subset using only open-source models. Its automated generation pipeline achieves more than 81% tool executability and up to about 69% task completion on Agent Gen 80. The practice module yields roughly 5 to 7 percentage point gains on AIME with just 100 examples and around $18 of compute. And the RL module both speeds up training by 40% and lifts Qwen 2.57b from 10 to 45% accuracy on AIME 2024. Despite the progress, there are clear limitations. Automated generation doesn't yet solve all tasks. Roughly a third of Agent Gen 80 tasks still fail end-to-end. The RL and practice modules are mainly demonstrated on math and QA, so generalization to other domains needs more work. And while the authors mitigate entropy explosion, long horizon stability in complex environments is still a challenging open problem. Looking ahead, they plan to integrate more environments, strengthen multi-agent collaboration, and design richer strategies for accumulating and reusing experience. Youtu-Agent is an attempt to close the loop between how agents are built and how they learn. By combining automated configuration, training-free practice, and scalable RL, it shows that open-source agents can be both competitive and evolvable. For practitioners, it offers concrete recipes and code to build real systems. For researchers, it provides a testbed for studying automated agent design and hybrid policy optimization. It doesn't fully realize agents that design and train themselves yet,